Welcome to the 34th lecture of graph theory. Today we will talk about feasible circulations. So, here feasible, when I say feasible, we have a directed graph and then with each arc we are associating two real numbers. So, let us say B of A and C of A. B of A is a lower bound, C of A is a upper bound, which means that lower bound for the circulation value on that arc, and of course, B of A has to be less than or equal to C of A. Now, a circulation f in D is called a feasible circulation with respect to these functions f, B and D, B and C, if B of A is less than or equal to f of A is less than or equal to C of A for all A element of A. A feasible tension is defined analogously. For instance, we are given upper bound B and lower bound B and upper bound C. And now, the main topic that we will consider in this class is a necessary and sufficient condition for the existence of a feasible circulation in a network given the lower bound function B and the upper bound function C. What one can immediately see is this. For instance, as far as a necessary condition is like this. For instance, if you consider, suppose you have this graph and this is a subset X. Now, we know that because this is a value of the flow value here on this thing. So, what can I tell about f plus of x? That means the value of the flows on these arcs, the outgoing arcs, that has to be less than or equal to definitely C of x. This is the C plus of x, right. Now, on the other hand, we can say that f minus of x, that means say if you consider the incoming arcs, these are the incoming arcs for the x, right. The sum of the flow values on these incoming arcs has to be greater than or equal to B minus of x, because these are the incoming, whatever the lower bound, it has to be greater than. This is an two obvious things, but the interesting thing is that this quantity and this quantity are equal. That means we have f plus x equal to f minus x. So, therefore, we will get C plus x greater than or equal to f plus B minus x. Why is it so? Why is this equal? That is because if you consider this set x and then if you consider the vertices on this thing. So, these are the vertices. Now, if you sum up the flows on the every arc adjacent on each vertex, right, then what we get is, right, this if we take this sum, then what we will get is equal to the flow value on the outgoing arcs minus the flow value on the incoming arcs. Why is it so? For instance, when I sum these things, so we can say for each of these arcs we have the value of this one and value of this one, right, and this will contribute to, for instance, if I take an edge here, right, now this will contribute to the outgoing flow on this vertex, and this will contribute to the incoming flow on the on this for this thing. So, finally, when I consider the sum, right, for instance, sum over all vertices, this edge effect will cancel off. In other words, so for each v element of x, if I sum over f of so let us say these are we'll do like this. Suppose this is u1, u2, u3, u4. So, if for a vertex what I am summing up is the flow value on v u1, all the outgoing arcs minus sum over and then minus the sum over flow value on say u1 dash comma v, right. These are the contribution due to the incoming arcs. In other words, we know that because it is a circulation, this sum should be 0 for a vertex. So, we sum up over a vertex all the flow values on the incoming arcs and minus the flow values on the outgoing arcs. This being 0, the total has to be 0 here, because each vertex will contribute a 0. But on the other hand, if I take a edge in such that both these endpoints are inside x, then this edge will contribute to the positive term of this vertex and negative term of this vertex. Therefore, this effect of this edge will be cancelled in the total sum, overall sum. But on the other hand, if I consider this edge, this will be in the positive term of this vertex, but because this vertex is not there in x, the negative this is not added in the negative term. So, therefore, this will remain. Similarly, if I consider this incoming edge, this will be in the negative term. So, finally, when I sum over all vertices, what remains is the f plus of x minus f minus of x. This is what will remain. But this has to be 0, right, because the overall value is 0. So, we get f plus of x is equal to f minus of x. But now we know that we have already seen that f plus of x has to be greater than or equal to has to be less than or equal to c of a, and f minus of x has to be greater than or equal to c of c plus of x and this b minus of x, right. So, what we get is c plus of x has to be greater than or equal to b minus of x for every x subset of v. This is a necessary condition for a flow. This is a necessary condition for a feasible circulation, right, if the circulation is feasible, because we know each flow value has to be less than or equal to c of a for each edge and greater than or equal to b of a for each edge. Now, we are going to prove that if for each subset x this condition is satisfied, then there exists a feasible flow in the directed graph. how do we show this thing? So, this is to show this thing. So, so this is this theorem due to Hoffman. It is known as Hoffman circulation theorem, and this is about the necessary and sufficient condition for the existence of a feasible flow in a digraph given lower bound function B and upper bound function C. It says that this condition, that is for each subset x of V, our upper bound C plus x has to be greater than or equal to the lower bound B minus of x. This is indeed the condition for the existence of a feasible flow in this graph. What we have just now seen is that if this condition is satisfied, then there is if this condition has to be, if this condition is not satisfied, we cannot have a feasible flow. In other words, if there is a feasible flow, this condition will be satisfied. On the other hand, we will show that if this condition is satisfied, then we can indeed get a feasible. How to get a feasible flow, we will show. The other part of this theorem says that if B and C are integral valued and satisfying this inequality, this condition is satisfied, then D has an integer value feasible circulation, not just a circulation, it has an integer value feasible circulation. This is what we are going to do now. The proof is done like this. First, we consider a function f, and we, rather than making it a circulation, we would rather make it feasible first. In other words, for each arc A, we will define the value f of A to be in between C of A and B of A. This is quite easy, because we know by definition B of A is less than or equal to C of A. There is something here, we can always place get a value in between, and then we place it here. Suppose if this and this are integers, we can always take an integer value itself which is in between this. For each arc, we will select the value of f to be something in between B of A and C of A. Now, we have made it feasible, but it need not be a circulation. For a circulation, what is the condition? For each vertex, the sum of the flow on the incoming arcs has to be equal to the sum of the flow on the outgoing arcs, right. This should be equal to this. Now, what we can see is that each vertex, if we check each vertex, there is this outgoing arcs for each vertex, right. So, we can sum up the values on these arcs, and we can sum up the values on these arcs, and this minus this we can consider. Now, if this is equal to 0, that means as far as this vertex is concerned, this function f behaves like a circulation as far as this vertex is concerned, but it need not be 0. It can be more than 0, it can be less than 0, it can be positive or negative. If all are zeros, for all vertices this value is 0, then we can say that it is indeed a circulation, and then we have got a feasible circulation, because we have selected the function values to be such that it is in between lower bound and upper bound for each arc. Now, we can assume that, so it is not like that. There are some vertices with positive x's, we can say that it is x's, right, and some with negative x's, right. So, is it possible that all of them have only positive x's, whenever there is an x's it is only positive? It cannot be so, because if you sum up over all vertices, as we have already seen, each edge will contribute, say for instance this edge if I consider, this will contribute to the positive term of this vertex and the negative term of this vertex, therefore, it will cancel off. Finally, we have to, when you sum up over all vertices, the flow on the outgoing edges minus the flow on the incoming edges, this total sum has to be 0, because every edge contributes once to a positive term, once to a negative term. So, therefore, they cancel off, right, positive. So, therefore, total has to be 0 anyway. So, therefore, it is not possible for some vertices to have only positive excesses, well no negative excess. So, if there is a vertex with positive excess, that may be incoming total, sum of the incoming the flow on the outgoing edges minus the sum of the flow on the incoming edges is positive for some vertex, then there should be some other vertices with this value negative. Now, whatever is the excess, we can consider as a measure of the overall deviation from what we aim. What we aim is every vertex to have 0 excess, right, that means it is a circulation. So, this deviation whether negative or positive, we can consider its positive part, that means the more absolute value, and we can call it as the and the sum of these absolute values can be taken as the total excess. Now, what we do is we are going to demonstrate a method by which we can modify the value of the flow on the arcs of this network, or maybe on some arcs of this network, in such a way that we will get a new flow. But when we are doing this, we will make sure that the new flow values, so the the value of the functions, we cannot still call it as a circulation or flow. So, we will say that the new function value is again feasible, that means for every arc it is in between the bounds, that means in between the lower bound and the upper bound. While the progress we will make is that with respect to this new function, the total excess, the sum of the absolute values of those excesses on each vertex will be less, will reduce, it will come down, down, down. Every time there is an excess, we will show that we can make some progress like this. So, until the excess becomes 0, that means we end up with a circulation, feasible circulation. This is the aim. So, we just have to show how, suppose there is a positive excess, total excess, then how we can make a progress such that after changing the function with respect to the new function, the total excess is strictly less than the old total excess. To do this thing, what we do is we consider any vertex with say negative excess, say this is a vertex u, and when I consider the sum of the flow values, the function values on the outgoing arcs minus the sum of the function values on the incoming arcs for this vertex, it is a negative value, let us say. Now, we will define something called an improvable path from u. This is like the max flow min cut, the proof of the max flow min cut theorem that we had done earlier. So, what we do? We will consider any path such that, suppose if it is in the path starting from u, if it is a forward arc, what we will see is whether the current value f of this a is strictly less than the upper bound, that means c of a, whether the value of the function now is strictly less than w, then it's okay, it's an admissible arc. On the other hand, suppose if it is like this, if the arc is like this, what we will see is the value of the function is strictly greater than b of a. This is what we look, whether this is strictly less than c of a or this is strictly greater than b of a, right. So, now for in other words we will collect starting from u. See, remember this is negative x's, here it is a negative x's, then we will find out all the vertices which can be reached from u via some feasible via some improvable path. These are called improvable path. To repeat, what is an improvable path? Improvable path is a path starting from u, and each edge on this path is such that if it is a forward arc in the path, means going outward from when we are traversing from u, if it is a forward arc, then the value of the current function on this arc will be strictly less than the upper bound for that arc, and if it is a reverse arc, the value of the function will be strictly more than the current arc in this function. Now, what can we infer about, suppose x is the set of vertices which are reachable from u by some improvable arcs. These are the vertices. There can be some vertices outside also, right. Now, there can be some arcs which are going from x to outside, right. What can I tell about it? If it is a forward arc, if it is an arc going from x to outside, then what can I say about the function value here? So, then this f of a equal to c of a, right. Otherwise, if f of a was strictly less than c of a, then we could have got this vertex also in x, right, because this vertex is reachable from u via an improvable path up to here, and then we could have used this to get in. So, that means if it is a forward arc, if it is an arc going out of x, then it is clear that the current function value at this edge is equal to c of a. On the other hand, if we have an arc like this, incoming arc from outside to, then what can we say? Then f of a has to be equal to b of a. That is why we cannot use this arc to go out and capture this vertex, right. So, this we have seen in the case of max flow, the proof of max flow Minkert, slightly different, but then more or less the same idea, right. So, these are the improvable paths. So, therefore, we have this setup. So, whenever it is an incoming arc, f of a value is equal to b of a there. Whenever it is a outgoing arc, the function value is equal to c of a there. Now, as we know, if you sum up the excesses over all these vertices, that means the sum of the function values on the outgoing arcs minus the sum of the function values on the incoming arcs over all these vertices, right, inside x, what will we get? As we have seen, the edges which have both its endpoints inside x will not contribute to this sum, because for one vertex it will contribute to the positive term, and to the other vertex it will contribute to the negative term. Therefore, we know that the only contributors are the edges which are going out of x or coming into x, namely the f plus x and f minus x, and this total value will be f plus x minus f minus x. So, if you sum up the excesses over all vertices inside x alone, what will we get? F plus x minus f minus x. But then this f plus x is equal to c plus x, because for all the outgoing edges the function value is equal to c of a there, right, for that particular arc which is going out. We know that it has touched the upper bound. Therefore, this will be equal to c plus x, and this will be b minus x, because each of the incoming arcs the function value is touching the lower bound. And because of the condition that c plus x is greater than or equal to b minus x for each subset x, this has to be greater than or equal to 0, right. So, the greater than or equal to 0 is the when you sum up the x's over all vertices in x, what we get is going to be a value greater than or equal to 0. It can be positive, it can be 0, no negative, not negative. But can it be 0? No, it cannot be. No, it can be positive or 0. It can be 0. It can be positive or 0. It cannot be negative. But on the other hand, within x, we know we have this u, and its axis is negative. So, one of them is negative, but the overall the thing the total sum of x's has to be 0 or positive. So, that means there should be at least one somewhere in x, maybe this one, say v, such that its axis is positive, right. It should be there, otherwise how can the total be non-negative. So, because there is one negative, there should be one positive at least. So, let us take u and v, and also v is part of x. So, there is an improvable path from u to v, there is an improvable path from u to v. Let us consider this path. So, this is u and here is v, and let us consider this improvable path. It can be something like this, some are positive, some are negative, right. So, it can be that. Now, what we do is, this is an improvable path. The function values at each of these things is if it is positive, it is strictly less than its upper bound. If it is reverse arc, then function value is strictly greater than its lower bound. What we do is, whenever it is a forward arc, we will increase the function value by 1 plus 1, here also plus 1, see. But whenever it is a reverse arc, we will decrease it by minus 1. See, remember, this f of a is also an integer value, b of a and c of a is also integer value. See, we can always do the things without integers also, but to explain the idea, we can assume that it is b, c, everything is integer, and then we started with an integer valued f. So, we will increase plus 1 for the forward arcs, decrease 1 from reverse arcs, and all other arcs we will leave it as such. Now, we can easily check that for these vertices, the interior vertices, the increase and decrease overall balances, because there is no change for the x's. The x's will not change. Why? For instance, if a vertex sees 1 here, then here both cases we have increase plus 1, but then this is an incoming arc, this is an outgoing arc. So, from the outgoing arc also there is an for the sum on the outgoing arcs also we have a plus 1 increase, for this incoming arcs also we have a plus 1 increase. So, the total is going to remain same. On the other, similarly, if it is like this, same situation, both is a negative, right, both minus. So, for incoming arcs also one is reduced, for the outgoing arc also one is reduced. And in this case, if it is like this, for instance, then here is a plus 1, here is a minus 1. So, you can see that both are incoming arcs here. So, 1 plus 1, 1 minus 1. So, it is like incoming a total sum on the incoming arcs is changed by 0, right. Similar situation if it is like this, both are outgoing arcs. So, this will be minus, this will be plus 1. So, total it would be like the total sum on the outgoing arcs have increased by 0, nothing, right. 1 plus 1 and 1 minus 1. So, therefore, the interior vertices of the paths will not have any change in their axes, but here we know that clearly there is a plus 1 increase, here there is a minus 1 decrease. So, plus 1 increase or 1 decrease, right. So, this adds minus 1 and this is plus 1, because this is an outgoing arc here, only outgoing arc is there, this only incoming arc is there. But this was a negative excess already, plus 1 increase will only, the absolute value will only reduce here, that is the important thing, because this is already negative. When you add plus 1 to the excess, the absolute value reduces. Similarly, here this is a positive, this is a positive one, and when I decrease, the absolute value reduce. Here also the absolute value of the excess reduce, the absolute value of the excess reduce. The total absolute value of the values of the excesses reduces then. So, therefore, we know that the excess has reduced. So, that is the key point here was to start with a vertex with negative excess, which was guaranteed because the total has to be 0. Total sum of the excesses has to be 0. It is not possible to have only positive excesses. If there is no negative, then there is no positive also, everything will be 0, then we do not have to do anything. So, now once we selected u with a negative excess, we just wanted to select another vertex v with a positive excess, but also reachable by a improvable path. That means, a path where each edge is such that if it is a forward edge, it is strictly less than the upper bound. If it is a reverse edge, its value, the function value is strictly greater than its lower bound, and we have shown that it is possible. So, therefore, this procedure can be repeated, and then finally, the total sum of the absolute values of the excesses will come to 0. At that time, we will get the feasible function, which is also a circulation. So, this is this explains us why that condition that C plus of x greater than or equal to B minus of x for every subset x of V is not only a necessary condition, but also a sufficient condition for the existence of a feasible flow, right. So, if such that condition is satisfied for every subset, a feasible flow indeed exists. We have demonstrated how to get one feasible flow. Now, that is we will now there is an equivalent theorem in the case of tension also. We will not repeat all the things again, but we can see that in the case of tension, the place of cuts is taken by cycles. So, we can consider a cycle, and we can show that the if you consider a cycle and associate a certain direction to this, C minus is the reverse arcs with respect to the sense of direction we gave on that cycle, and B of C minus has to be less than or equal to C of C plus. This is a necessary condition, right. Now, this necessary condition is also sufficient. It was proved by and that is also proved, and this is this theorem. So, but we will not get into the details of this. Anyway, that is very much similar to the theorem that we have seen. Now, we will go to a different topic here in the flows, because in this class we have to finish flows. Therefore, we will quickly cover some more topics, so that even if we are not doing all the proofs, at least to see some concepts. Now, let us consider what is a nowhere zero flow, nowhere zero circulation. So, consider f, or maybe we can in general consider a function defined on the arc set of A. It is called the nowhere zero if for each arc f of A is not equal to 0. That means, if I consider the support of this function, then that is the entire arc set itself. There is no arc for which f of a is equal to 0. That is a very intuitive definition. Now, we will define something called a k flow. A circulation is called a k flow if for each arc its value is in between minus of k minus 1 and plus k positive k minus 1, in between minus of k minus 1 and k minus 1. So, for this k is, we will take it as k greater than or equal to 2 flow. So, otherwise it is it has to become 0. If you put 1, it has to become 0. So, 2 onwards, right. So, in between, because remember this is an over 0 circulation. It has to be, first important thing is it has to be an over 0 circulation. So, one it's a historically it is called a k flow, though it is actually a circulation. So, but it is let us conveniently use this word k flow to denote this thing. For instance, if you are talking about a 2 flow, we want the values of the function, the circulation to be minus 1 or plus 1. Of course, the values are integers. We are not allowed to use fractional values or real values. So, all the values are function values are to be from set. For instance, if it is k equal to 3, that is minus 2, minus 1, 1 or 2, these are the allowed values, right. For each arc, the value of the circulation should be minus 2, minus 1, 1 or 2. So, this is what a k flow is. Now, very interesting thing is you can define a circulation over set k. What do we mean by that? So, the values are 0 over 0. So, 1, 2, 3, 4 up to k minus 1 set k, right. The summation is now done modulus mod k, right. It is not the usual summation. We will sum and take the remainder with respect to the mod k. So, this way also we can define. So, this is somewhat different because now the main condition for the circulation was that the sum of the flow values, the circulation values on the outgoing edges should be equal to the sum of the flow values on the incoming edges. But you see here the actual value need not be same, but it need not need to be same. The sum of these values, say suppose this is k f1, f2, f3. So, f1 plus f2 plus f3 has to be equal to, say this is f5, f6, f7, f8. So, f5 or okay, maybe to be consistent we can say, now let us do this. It can be like, let us say this is A1, this is A2, this is A3 and these are say A4 and A5. Usually we want f of A1 plus f of A2 plus f of A3 equal to f of A4 plus f of A5. Why? Because this A4 and A5 are the incoming arcs, A1, A2, A3 are the outgoing arcs. Now, we do not want this, we just need this mod k only. So, when you, this may be different values, but when you divide by k and take the remainder, they has to be same, right. So, therefore, somewhat different this flow, but the interesting fact is that a graph admits an over 0 circulation over set k if and only if it admits a k flow. It is one side should be same, because for instance if I have a k flow, then I can show that there is a set k flow also. Why is it so? So, one way of seeing it is, so for instance you have, after all we can interpret each of this values plus the integer values in between minus k 1 minus 1 and to plus k minus 1 as the values with respect to in that set k, in set k, and then if you sum up, that will, because when for our flow it is equal to 0, then naturally this will, with when you take with respect to mod k, that will be equivalent. So, one side is definitely same. For instance, if you let's definitely easy, for instance if you have a k flow, then we do have a over 0 circulation over set k also. But on the other hand, that is more non trivial. For instance, how can we say that suppose this condition is satisfied, that means with respect to this mod k the equality is satisfied, the actual equality can be obtained for some slightly modified flow. So, we can, to show this thing, we can use the similar trick that we have done in the earlier case. Suppose let us assume that we have a flow in the set k world, right. The values are the function, it is a circulation in set k, and then now we can again define this notion of excesses, right. So, you know every excess is a multiple of k now, because when you take this, if you consider it as usual integers, though not in the mode set k world. So, if you take the sum here and minus the sum here, like the sum on the incoming edges minus the sum on the incoming, we can again define the excess here. This excess is definitely divisible by k. That is why it is when I take the difference, it should be 0 mod k. So, therefore, it is divisible by k. So, but as before, we can consider it as a positive excess and negative excess and 0 excess, and then we can try to reduce the total excess, so that finally the total excess will become 0, like we did in the other case. So, for instance, we can see if all are not 0 already, in that case we are already done. So, if there is a positive, suppose we can, if there is a positive, then there should be a negative, all cannot be positive alone, because again if you take the total sum of the excesses, it again has to be 0, like we explained in the earlier case, right, because every edge contributes to one positive term and one negative term. Now, so we can consider, start with a u which has a positive excess this time, say, and then we can consider all the vertices which are reachable from u by a directed path. This time we are not allowing any this notion of path we are taking is different, we are taking directed paths, not allowing any reverse edges. So, all the vertices which can be captured using directed paths starting from u. Now, we collect all the vertices, let it be x. Now, you know any edge which is going, so which has some interaction with outside world should be incoming edges only, that is why we cannot go and capture the remaining ones, right, it should be like this, it should be, everything should be like this, incoming edges. Now, we know if you sum up the excesses over all these x's, that as earlier it has to be f plus of x minus f minus of x, we are not repeating the argument here, and this f plus of x is not there at all, because there is no outgoing edge, because if there is an outgoing edge we can capture the endpoint of that outgoing edge also. From u you can reach to that vertex also via directed paths. So, this is not there. So, minus of f minus x only is there. So, this has to be a negative value, right, this is less than equal to 0. So, now u has a positive excess, the total sum of the excesses on the vertices for the vertices of x is less than equal to 0. So, there should be one with the negative excess. So, let us call it v, this is u, this is v, this has positive excess and this is negative excess, and then there is a directed path, and also there is a directed path from here to here. Now, what will you do? So, we consider like this. So, this is a direct path from this thing. We consider changing the direction of the edges here, and then we can assign the value k minus f of a for each of them. So, if f of a is the value here, put k minus f of a here for each of them, right, the corresponding f of a value k minus this thing, and now for all other edges we will keep it same. Now, we can see that the excesses for all these things are not changing, while this thing we have a decrease of minus k. Here this thing the excess will increase by so decrease by k here and increase by k here, because this is a negative excess, the increase will cause the absolute value to decrease. So, the total increase in the sum of the total absolute values will be now by 2k, right, plus 2k, sorry, total decrease. So, here, so this is a positive excess, here is a decrease, here is an increase. So, totally there will be a decrease in the total sum of the absolute values of the excesses. So, I just leave it to the students to figure out that this indeed happens. So, see why I am leaving it is because this is more or less the same trick that we have done in the proof before. So, when we considered the existence of the feasible flow. So, just that the only concept was there we were using a kind of improvable path specially defined. Here we are just taking directed paths, all the other ideas are more or less same. So, and then we are just bringing the total sum of the absolute values of the excesses to 0. So, therefore, we can do this thing, and finally, by repeating this procedure we will come up with a flow where all the excesses are 0, which means that it corresponds to a usual k flow. Now, when we come to k flows, the next main concept is the flow number. The question is, so given a graph, what is the smallest positive integer k for which it has a k flow? So, why am I talking about a graph, not a digraph now? Because the orientation does not matter anymore. So, for example, suppose you have an edge here. So, you have a graph and then each edge is given a direction, and then there is a k flow. Then we can show that for any different orientation also we have a k flow. The reason is we can just suppose for this edge, if I reverse the direction and put the negate the flow value here, then it is still a flow, right, because for this and these are the only two vertices which are affected. Here earlier it was a outgoing edge, but now this is an incoming edge, right. So, therefore, when you negate the thing, the total incoming value will be reducing by that quantity, because there is a negative value here, while earlier there was a positive outgoing edge, the corresponding positive value is now not there, therefore, it balances. Similarly, for this edge. So, therefore, it is still a circulation. So, if we have a k flow for a given orientation, for any other orientation we can get a k flow, a different k flow with either just by negating the flow values, right, in corresponding, whenever we change the orientation we negate. So, the orientations are not very important when you talk about the existence of a k flow. We can, if we say that for this, we can simply say that for this graph there exists a k flow. So, in other words, we say that whichever is the orientation, we can find a k flow. So, therefore, we can talk about, given a graph, the smallest integer k for which any orientation of that has a k flow. So, some simple examples we can consider. A graph, when this a graph admits a 2 flow, the simplest, the smallest possible value is 2. So, it is that is even only if it is even. For instance, if it is an even graph means every vertex has degree has its degree equal to an even number, then it is very easy to see that you can give an, you can get a 2 flow for that. 2 flow means the values allowed are just 1 or minus 1. How do you get a 2 flow for that? So, just first give a even orientation for that. Even orientation means for every vertex we have to give incoming arcs and outgoing arcs, numbers are to be equal. How do you do that? You can consider an Euler tour of the graph and then give the orientations with respect to that. That means, as we traverse the Euler path, give the directions, right. So, every vertex will have equal number of incoming edges and outgoing edges. So, then if you give 1 1 1 for every edge, then indeed the total on the incoming edges will be equal to the total on the outgoing edges. Therefore, it will be a circulation, and also it will be a also it will be a feasible, sorry, a 2 flow, because the 1 is in between minus 1, the flow value should be in between minus 1 and 1. So, 1 is an allowed value. On the other hand, we can also show that suppose there is a 2 flow, it has to be an even graph. So, you can consider any orientation for which there exists a 2 flow, and then what we can do is whenever the flow value is -1, we reverse the orientation of that edge and then make it +1. So, all the flow values can be considered 1 now. Now, it is very easy to see that for every vertex all are 1, right. So, it is very easy to see that the number of incoming edges is equal to the number of outgoing edges. Otherwise, how is it possible that the total on the some of the values on the outgoing edges equal to the sum of the values on the sum of the values on the incoming edges. So, for that the only way is the number of incoming edges equal to the number of outgoing edges, if all values are 1, right. We can, because the only allowed values are -1 and +1, whenever there is a -1 we just reverse the orientation of the edge and make it +1. We know that this can be done, this is still a circulation, right. That is what I explained just before. So, now therefore, the total will remain circulation. So, we see that if there is a 2 flow, incoming degree has to be equal to outgoing degree, which means that when I remove the directions, the degree of each vertex has to be an even number. Similarly, another statement we can make about it, this thing is any 2 edge connected cubic graph. So, 2 edge connected is required, because if there is a bridge, as we have seen, it is a cut just one edge, it has to be 0, right, because we are talking about nowhere 0 flows. Therefore, 2 edge connectivity is a must. So, 2 edge connected cubic graph admits a 3 flow if and only if it is bipartite. So, now we do not have time to do the proof, therefore, we will keep it for the student to work out. And finally, we conclude with the 3 famous conjectures from Tutte about the flow number of graphs. He says every 2 edge connected graph admits a 5 flow. This is the 5 flow conjecture. It is known that every 2 edge connected graph admits a 6 flow. Whether it admits a 5 flow or not is still open. The 4 flow conjecture says every 2 edge connected graph without a Petersen graph minor admits a 4 flow. And the final third conjecture, the 3 flow conjecture, every 2 edge connected graph without 3 edge cuts admits a 3 flow. So, these are very significant open problems in graph theory. So, with this thing we will leave the topic of flows, and in the next class we will consider the application of probability in graph theory. Thank you.